Hi guys, I'm Heng Jim Cheng from School of Physics, Year 1 studying in Engineering Physics.
Hi, my name is Ng Zizwan. I'm from the School of Physics, majoring in Engineering Physics, and I'm a first-year student.
I'm Ang Bing Jung from School of Physics. From sundials to hourglasses, then to pendulum clocks, we now have the most widely used and reliable clock, that is, quartz clocks. But the question is, are quartz clocks really reliable enough? In every modern clock, the timekeeping element is a harmonic oscillator, a physical object that oscillates at a constant rate. One of these objects, of course, is quartz, silicon dioxide. It is what is known as a piezoelectric material, that is, when subjected to mechanical stress such as bending and heating, it produces an electrical charge. As with materials exhibiting the piezoelectric effect, it also exhibits the reverse piezoelectric effect. That is, when an external electric field is applied to it, it vibrates at very precise frequencies. Shaped like a tuning fork in a quartz clock, when the current from the clock's battery is passed across it, it vibrates at exactly 32,768 Hz. However, over time, a quartz clock loses accuracy because the frequency of quartz oscillation decreases over time, and a proper voltage is needed to correct its frequency. Temperature and pressure changes can also alter the frequency of the quartz oscillations. This is where cesium atomic clocks comes in. Cesium-133 atoms exist mostly in two hyperfine ground states, one with a lower energy and the other with slightly more. These two states of cesium-133 atoms can be separated by magnets. The lower energy state atoms can be excited to a higher energy state when irradiated with electromagnetic radiation of the right frequency. Now we will use a simple model of a cesium-beam atomic clock to demonstrate how atomic clocks work in general. Firstly, cesium-133 atoms are passed through a magnet to discard the higher energy state atoms. To allow the lower energy state atoms to be passed into a chamber in which they are irradiated with electromagnetic radiation of the right frequency to excite them to a higher energy state. These excited atoms are then passed through another magnet, this time discarding any lower energy state atoms while directing the higher energy state atoms to a detector. The frequency of the electromagnetic radiation is controlled by a quartz oscillator. As long as the quartz is oscillating at the frequency which sets the electromagnetic radiation to the right frequency, the detection of the excited atoms continues at the peak rate. When the frequency of the quartz oscillation decreases, the frequency of the electromagnetic radiation changes as well. Fewer detections are made, which tells the electronics to apply a proper voltage to the quartz to correct its period of oscillations, thus creating what we call a feedback loop. This enables the cesium atomic clock to be self-correcting. So you might wonder why accurate timekeeping is so important. More accurate timekeeping than that by a quartz clock has many importance, such as within scientific studies at CERN, where incredible precision is needed to sync the atomic smashing instruments. The probably most commonly known use of accurate timekeeping is in the Global Positioning System, or GPS. For GPS satellites to work out precise location, the timings of the signals that they send and receive must be just right. As the signals travel at the speed of light, therefore, an error of even 1 microsecond translates to an error of 300 meters on the ground. Accurate timekeeping is significant due to the need of standardization in scientific studies. Atomic clocks nowadays deviate only 1 second in up to 100 million years. The high-level precision and reliability make atomic clock a suitable frequency standard to define 1 second as the SI unit of time. 1 second is defined in the International System of Units as the duration that elapses during 9,192,631,770 cycles of radiation produced by the transition between two high-refined levels of the ground state cesium-133 atoms. Atomic clocks are designed to detect this frequency. Most of them today use atomic fountains. Think of it as a cloud of atoms that is tossed upward by lasers in Earth's gravitational field. International atomic time is determined by atomic clock as well. International atomic time is a timescale that uses the combined output of some 400 highly precise atomic clocks. It tells us at which speed our clocks should tick. To summarize, accurate timekeeping is a necessity in many time-sensitive technologies, such as in global positioning system. The working principle of an atomic clock demonstrated and highlighted the unique and intricate intrinsic properties of atoms and their electromagnetic wave associated with the electromagnetic spectrum of atoms. This ingenious application should be appreciated by all. Thank you.